Continuing with our presentations on Lecture 15X, page 2 for descriptive inorganic chemistry, let's consider iron 3 nitrate. The bad boys, the bad girls. Number 9, trend. I would suggest you look at figure 5.6 of Weller's book that we use. And we talked about that before break, and we outlined a periodic pattern. The problem I have with this figure is I don't know of iron plus 4. It's listed in the table. I kind of doubt that behavior. But anyways, let's move on. Iron 3 nitrate. What does it do? What is it? Well, iron 3 means iron 3. Nitrate ion. Oh, nitrate is on our spectator list. So does it do anything in water? No. So it's neutral. Remember, it's one of the 7 anions that we consider spectators because it's a conjugate base of a very strong acid, nitric acid. That's why we consider its base properties very, very weak. I.e., again, it's Kb modeled as 10 to the minus 18 if we level things in water, if we use that model, for example. Okay, let's look at iron plus 3 now. You can also look at the handout because there's some various models you can use for this. So there's multiple possibilities, which I like about this problem. Okay, iron 3 aqueous. All nitrates are water soluble. They are typically strong electrolytes in water. And ionic compounds are always considered strong electrolytes. Okay, so let's look at iron 3's behavior. We're focusing on this guy now and not doing the dissolution and dissociation, all that. So iron plus 3 could be modeled a couple different ways. One of the popular ways is iron 3 as the hexahydrate. Simple naming terms. So what does this guy do in water? Well, that's what we're suggesting. We have here is an octahedral presentation of the water molecules around iron. We've talked about that once before. So let's go ahead and look at water. So this guy, so we're saying, is the iron 3 an acid? Is it amphoteric? Is it basic? That's what's bad about the bad boys and bad girls. Okay, so let's model this guy on. If we look at figure 5.6 from Weller's book and from what we mentioned in class previously, this guy is a indirect ironIII acid. In other words, it's going to give me a hydrogen ion or a hydronium ion, which we're modeling as equivalent. If we look at their K value for the transition between those, we give it as 1. If you can look at the reference table. Okay, so let's look at this guy, plus water. So if it's acting like an acid, what we do is then make hydronium ion aqueous. And what that means is there must be a hydrogen that's kicked out here. So it's not obvious a direct ironIII acid, but it can be considered a Bronsted-Lowry acid because it transfers a hydrogen ion from itself to the water molecule. So we haven't looked at the Ka for this guy. But then I have hydronium ion. And then what do I have now? This is kind of tricky. but there's some additional stability. Iron likes hydroxide. And what I have now is I have 5 waters. Okay. And then what I have is a +2. And if I notice, I got charge balance on the right, +3, and I got +3 on this side. That's kind of getting us ready for redox equations coming up. Okay, so it's nice to have a reference table, and I do have reference tables for the transition metals. This guy, this Ka1, because this could happen once, is approximately 10 to -3. It's considered a moderate acid. So I need some reference, i.e. table, or of Ka values, or I need a figure that represents the pattern to predict, especially transition metals. Most of the time, we think the transition metals hydrolyze water, break it apart differently in this case, and it makes an acidic solution. Is that always true? No. But in the chemical sciences, we watch out for putting transition metal salts into metal vessels because we can corrode them by different routes. Okay, so another way we could model this, I don't want this video to get too long because it's hard to import these guys. Let's look at iron +3, aqueous, +3 waters, and you say, why is that true? Well, this is one of our other models, and I heat it up a little bit. You can actually go in the lab and observe this. What you actually do is get iron-3 hydroxide. Solid. Could be colloidal suspension. It's involved in the rusting process. So if that's true, I get 3 hydroxides. That means I'm breaking the water molecule apart. That means the hydroxides, I got 3 of these guys, go to the iron. That means I'm left with 3 hydrogen ions. So if I'm looking at this model, I'm getting a lot of hydrogen ions. That's why we think this guy behaves very acidically. Okay, different than the handout. Other videos cited in the handout, some really good videos I cited on the handout. Have a good day. Bye.